Well, good afternoon, and thank you very much to the organizers for inviting me to participate in this wonderful session. I have to say right off the bat, Alberta, you guys are awesome. What vision! The LiDAR coverage in this province is tremendous. I am really green with envy, and sort of echoing sort of what Andy was saying, that the opportunities that you guys have in front of you are phenomenal. What I am going to talk about is this whole idea of looking at the point cloud data and trying to help inform decision making, because ultimately that's what it's all about. Boy, people are spread all over. I'll try not to put my back to anybody. What I'm going to try to do for this next hour is look at opportunities for LiDAR in government and industry, but then I want to focus more on the forest side, because that's kind of what the focus of this afternoon session is. And I want to try to walk you through how we have looked at processing and building LiDAR models for forest inventory purposes. And a lot of this is going to follow up on what Chris has spoken about, what Nicholas has spoken about, and what Andy's spoken about, and a little bit different flavor than how we've been doing it in Ontario, but generally the same approaches. So by the end of the day, you will walk out of here with the expertise to start this tomorrow. The other thing I want to bring to the table is how good are the results. So we can make all kinds of pretty rasters of lovely colors. I want to try to give you some feedback on what we're finding from our industrial clients on how well the inventories are working. The last piece I just want to touch on, if I don't talk too much about other things, I'm talking about this whole idea about LiDAR density. Somebody mentioned it earlier, same idea. We always think that more is better. Well, do we really need more dense LiDAR cloud to do better job at stand level, plot level based inventories? And we have some work in that area. And then finally, what I hope that you will be impressed about is a recent tool that's being developed as we speak, but I have outputs about to show you today about a decision support tool to support forest block harvesting calculations with a LiDAR based inventory. Sorry, I'm such a wanderer. You're frightened already. I think I want to talk about all these different opportunities, and I'm not going to. I want to pick on a few of them, but some of these are applications of LiDAR. Well, I'm going to back up. The LiDAR that I'm dealing with in Ontario is postage stamp size compared to what I used to be so proud. I'm working on $1 million and a million hectare LiDAR data set right now for one forest company. That's just like a little speck on your map. And so you guys have a tremendous opportunity. So everything I talk about here is more of an R&D sense. The things I talk about today are being operationally delivered in a forest inventory context for a forest company, but this is not what we're doing as a province. Okay? I think Alberta has the opportunity to maybe look at this, adapting some of these things we talked about, everybody's talked about today, in terms of doing inventory in this manner for the province of Alberta. So what I'm going to really hit from this list is, of course, the high-resolution DEM. But then I thought, everybody kind of saw enough of those high-resolution DEMs last night. So I thought, well, maybe I should change things up a bit. So we're going to look at some of my Christmas vacation photos instead. And then I'm going to talk about the landform classification effort that we're trying to do. We have an ecological land classification in Ontario, and we're trying to see how can we leverage the LiDAR data and that digital elevation model of high resolution to actually provide some predictive ecological land classification maps to aid our interpreters who are trying to do this as they do their soft copy interpretation for their FRI stand delineation. And I also want to talk about habitat modeling, because I think that's something that LiDAR has a huge opportunity to support, and I hope that you'll see some value when I present to that. And then finally, again, forest inventory, which is sort of what I do every day. So I forgot the photos because my wife would kill me if I did show them. What I'm going to look at quickly is this. This is a piece of real estate just east of where I work in Ontario, it's Champlain Provincial Park, and it's a forested area. And the digital elevation model that we have to work with in Ontario, or the majority of, especially the central northern part of the province, is a 20-meter product. And I can sense that I was in the basement here. There we go. It's like turning a light on. And it really is pretty impressive what LiDAR can do under forest canopies. And I think we've seen enough of these scenarios the last couple of days now to know that the potential is there. It's the potential that we want to talk about today is how to exploit this for further derivatives to support better decision making. In the case of forest industry, this particular one is in Timmins, if anybody knows Ontario, sort of northeastern portion of the province. Again, this is the exact same tile, and you can see the level of resolution that's available from that LiDAR-derived DEM. Now, from a forest company perspective, and I'm not in industry and I don't try to represent, but I'm going to parlay to you what they have told me, is with this level of detail in the digital elevation model, they are able to identify aggregate resources on the forest for road construction much easier than from the image on the left-hand side, the traditional OBM. And this is a clay belt site, so trying to find gravel for roads is very important. Also things like radio tower placement for communications. The reality is road layout for harvest blocks was manual, and this still is manual, but basically a guy would come with flagging tape, he'd have a map of the block boundary, he would head out there and try to find where to put the roads through. Once they saw the digital elevation model, all of a sudden there was a whole shift in culture. For these people that were basically, boots on the ground, they would not go do any road layout until they came to the office, sat in front of the digital elevation model with the mouse, planned where to put the road so they could minimize slope, minimize the angles on some of the corners. They would basically upload their Garmin GPS unit from the DEM product, and out they would go and they put the road in one day, first time, and they were done. Rumor has it, and I can't quote, what I've been told, is that the road construction costs alone paid pretty much for the acquisition of the LiDAR in this forest. And some of those other derivatives they were able to get from this digital elevation model. So that's pretty impressive. Looking at predictive landform and ELC stuff, we basically have in our possession very coarse North of Ontario Engineering Geological Terrain Survey maps. It talks about sort of the parent material. And we also have stuff that deals with landform. But what you look at the resolution that's available in those maps is not very detailed. So what we're looking at is taking the digital elevation model and using some tools, and in fact these are actually free tools, at trying to get at identifying different types. Of this particular one is the valleys and the lower slopes and the flat slopes and the middle slopes, and try to work towards the whole idea of predicting the landforms that are out there. And with the landforms, we have ground data, that we have sort of the soil texture information, and with some fuzzy logic models, we can actually extrapolate a much more detailed texture moisture regime map that basically provides the basis for our ecological land classification. So this is something that we're just heading into right now. Nothing really much more than that to show you. But we have done a little bit of validation in some of these tools, and basically going out and checking some of the threshold points that the models have indicated on some of these streams, these deeply incised streams, and where the edges of some of these slopes are. And this relates also to hazard mapping as well. Some of these tools from the digital elevation model are at your fingertips. And there are a whole bunch that are out there. And some of them are ArcGIS extensions, basically. And of course, ArcGIS is not so free. But the DEM surface tools you can download, ArcSIE, if anybody's familiar with SOLO, the Soil Land Inference Model at the University of Wisconsin, another powerful model. White Box is another free model from the university as well, from John Lindsay. A whole bunch of different tools that you can work with the digital elevation model. MicroDEM is actually an oceanographer tool, but it doesn't really know the difference whether it's the ocean floor or the forest floor you're putting in there. Sega is another very powerful free software tool that you can basically download tonight and start playing with your data tomorrow. So please give these some consideration. Split this is the LiDAR data cloud. We've seen this a few different times. I split the ground points out from the vegetation points. The ground points have basically been used to provide our digital elevation model. The vegetation points of what I want to focus on now, and what we've basically focused on the last few talks, is taking and exploiting that measurement of that forest structure into some tools that we can make some better decisions with. And in the past, as other people have mentioned, these vegetation returns were even not delivered to the vendor, or sorry, by the vendor to the clients. And so if you were flying LiDAR, you're basically flying up with a DEM in mind or digital surface model, and the LAS point data was not delivered. And so we've been working with people to make sure they get this level of information into some of the standards that Chris talked about before, so that we have a data set that we can do some pretty amazing things. And one is the whole idea of habitat modeling. And so we have a big species at risk program in Ontario where we're trying to delineate habitat for some of our species at risk. So some of these songbirds in southern Ontario, we looked at trying to identify with the experts and the biologists the type of habitat that these birds will have nesting sites in. And so this particular part is in Rondeau Provincial Park, which is in Lake Erie in southern Ontario. You can see that you can take that Lidar data, which basically measures that vertical structure so well, and bin it up into many different things. And we're basically looking at density on this bar chart on the bottom right hand side. We're looking at sort of vegetation returns by different height layers, which is what the classes, the biologists say, that are important for the bird species. And so about 100 meters away, we have another forest situation, which is very different. So that last one had some in that one point. Let me go back and just check. In this lower level, we had this vegetation. You sort of see we had all this sort of shrubbery in this point cloud. 100 meters away, we have a different stand condition where that's not present, but we have most of the vegetation occurring in these upper layers. Again, different type of habitat. With that level of information, or that type of information, with some of the other predictors that folks have talked about already today, we're able to do some logistic models, which basically look at probability of where suitable habitat for those species would be. Now, I'm not exactly sure how habitat modeling is done in Alberta, but in Ontario, we basically use age or inventory as our surrogate for some mental picture of what our forest stands will look like. I'm going to be really radical. I propose we get rid of age in an inventory. I'm going to come back to that at the end. How well is age referenced in your inventory? I want to talk about the Advanced Forest Resource Inventory Technologies Project, which is a project that's funded by the Canadian Wood Fibre Centre primarily. It has a whole bunch of partners in the bottom. Myself, Doug Pitt, sort of lead the Ontario effort, but we'll also work closely with some consultants, Margaret Penner, the biometrician, and Kevin Lynn of Lim Geomatics, who have sort of helped us move things through this process and helped us understand maybe some thinking outside the box on what's possible. I want to talk about an inventory project we did up in the Romeo Millette Forest, which is a 630,000 hectare forest. And it's basically a boreal forest, and we looked at 4 different types of a forest condition. We looked at the intolerant hardwoods, for sort of that poplar, white birch mix, mixedwood forest, jack pine dominated forest, and black spruce dominated forest. And we established 136 plots to build some inventory models, and we had another 138 plots established separately for our validation. We also had low density LiDAR, relative to Scandinavia for sure. We're not at 30 points, we're less than actually you have in Alberta. So another take-home message. Everything I talk about today, you can do here in Alberta. And I'm going to prove that to you. This, if you're interested, there was a paper published in August this year, the Forestry Chronicle, that talks about the whole inventory and the process that we used on the Romeo. I'm going to show you some graphics from that today. I want to talk about this. And I'm not trying to remove people from going to the forest. But let's face it, when we go out to do a stand inventory, what do? We sample. We do a very low intense sample. We wish we could do more, but we don't have the money. What we basically do, though, is we get very good estimates for where we sample. It's fairly expensive, and it's questionable sometimes how well that extrapolates across the land base. And if you have another stand that you're planning to harvest, you have to do it again, and again for the next stand. What LiDAR offers us is the opportunity. It is a sampling system, but it's 100% sample. It's 100% census of all that structure in that forest stand. And that provides us some powerful statistical predictions. So when we look at the stand, we have all the sort of vertical distribution all known for every spot in that forest. I want to quickly talk about this because usually when we talk about LiDAR, there's one big caveat in people's mind. Nobody can afford LiDAR, it's too expensive. That's in Ontario. Alberta is a much better place to come work. The other one is there's so much data we can't work with it. Yes, there's data, but you basically have to take a a divide and conquer approach to working with LiDAR data. And so one of the steps that we basically do, if this was, a forested area, 100,000 hectares or whatever, we basically tile our data up into 1 square kilometers. Now your data is already tiled, I believe, in its delivered state. But when you get to the LES data, basically push your tile data through. You can always mosaic it back to your area of interest. It's the products that you work with. It's not, 99% of the people are only going to work with the rasters that you develop. Only weird people like myself, there's a few of us in here, Chris, Nicholas, are working with the point cloud data directly. Most of the people just work with the raster. Some of that stuff can basically go out on your iPad in terms of working out in the field with it. So LiDAR data is manageable. It requires processing time. Man, we've become impatient. We want things instantly. So what if it takes your computer a week to process 1 million hectares of LiDAR data? That's 1 million hectares of LiDAR data you're pushing through a computer in a week. That's not too bad. Oh, and I work for the government, and if you really want to push LiDAR data through, or even image analysis stuff, go to Future Shop and buy a computer, and it'll probably be faster than what your government is. I want to quickly talk about the flow, and this is, I borrowed this from Kevin. I started to draft this out, and I remember that Kevin had done a similar flow chart for some work we did a little earlier, so I scooped this from Kevin Lim. Basically, this side of the flow chart is dealing with the forest plot data. So basically, put new plots in the ground, or find where you have existing plots in your land base, with your stratification, you measure your trees, you calculate your typical forest statistics that you want for your inventory, volume per hectare, PA per hectare, things of that nature. The other side of the equation over here is looking at your LiDAR data. So here we acquire LiDAR data. If you're doing a mission, you basically get your LiDAR data. You either classify your point data in terms of ground and not ground. In our case, it tends to be veg. Or your vendor delivers that. And then you take your ground points and you can tin it and have a tin surface. You can take your vegetation points over here, subtract them against that tin, and then you end up going, instead of having your point data being at 233 meters, it's 20 meters tall, bring it down to human Earth type units. At the same time, you want to intersect your field plot data that you have over here and extract the vegetation points that are represented in your field plots. So one of the things that nobody really hit about too much today is that you're looking at or have existing ground plot data that you want to build LiDAR inventory models for, you have to get good spatial position on those plots. Okay? 5 and 10 meter accuracy on the center of the plots won't cut it. You want to do sub-meter accuracy to help you build better models. There's another discussion about other issues to think about with plots. My pet peeve, if you have square plots on your land base, they're out there, use them. If you're going to put temporary plots in to do this type of work, use circles. You only have to GPS one point. If anybody's tried to GPS 4 corner posts, and you see the error, even a sub-meter, you never get a square. And sometimes I wonder, do you ever actually get a square out in the field as well? So that's just my personal bias after doing this for quite a few years. Calculating the LiDAR predictors, we talked a lot about that today, and go pretty quick. We've got to calculate the LiDAR predictors, that whole suite of predictors for every part of the landscape that I want to apply the models to, but I also want to do it for my plots that I'm going to build my models on. So now instead of that 1 kilometer tile, I'm actually breaking that 1 kilometer tile into 20 meter by 20 meter. We talked about that already earlier today. Why 20 by 20 meters? Because our plots are 400 square meter plots, and we're matching our model building area to our model prediction unit area as well. So we're keeping those the same. So that might be 625 square meters somewhere else. It could be 1,000 square meters. But you want to keep those units the same. Again, we have that for the plots and for the landscape area. You've seen this stuff already today, so I can just go really fast over this. There's all kinds of different statistical measurements. That skewness, the kurtosis, standard deviation of this spread. This is a plot here that's represented up here in this XY graph. And you can have percentiles and the density canopy metrics that you can feed into the models. We also have added some other things. We talked about that today through some of the other talks, like the crown closure estimates. We can feed that into our model. There's another one called vertical complexity index, which I'll talk about again in a bit. Other derivatives of that LiDAR density cloud can go into the model. The tools that are available to do that, well, sorry, I'm going ahead of myself. This is an idea of two different situations to stand and how two of those sort of predictors are related. So you can sort of see the point cloud on this upper one. And you sort of have this pattern, and you can see how the canopy density, the blue line that represents that structure, versus the one on the bottom, where you can see how the canopy density line represents that more open structure at the bottom, but a much heavier canopy. So this is how the LiDAR, these sort of relationships are representing those two different scenarios when we do our modeling. And how we get those predictors, we talked about Fusion a lot today, put it in there, it's probably the one that most people use. When we started this work a few years ago, we didn't look to Fusion quick enough, and we built some of our own tools, which is duplication of effort. So if you're getting into this today for the first time, you might want to look at Fusion. We basically have an in-house system that we built to meet our needs. And the other piece of software that we leverage is Q-Coherence LP360. Limitless LiDAR is basically an extension that goes into ArcGIS, and you can throw raw LAS data at that to your ARC's content, and you can do all kinds of filtering and classification and exporting into ASCII or shape files, whatever you want to do. It's not a free software, unfortunately, like $3,500 for that piece of software, but it allows you to bring, like in ArcMap 10, the LAS data. If you're still in a 9.3 world like I am, it probably will be for another 5 years in the Ontario government. We need to look for some other extensions to be able to handle the LiDAR data as a separate data. At the end of the day, you end up with basically a raster surface layer for every one of those LiDAR predictors. So the max height, the 90th percentile height, the density metrics, the skewness or kurtosis are basically raster layers, and they're all available there. They're all stacked up to build models. So the regression models is sort of the next approach. So you have your field plot data, and you have your point cloud data that you've extracted to represent that exact plot. Again, we're talking plots, we're not talking trees. We're talking that whole point cloud distribution that represents all the trees within that plot. We basically have that to develop our models. In terms of the inventory attributes we've been working with over the past 5 years, which continues to grow, this is out of our efforts on the Romeo Millette forest. We're looking at predicting that average height, the top height of the stand, quadratic mean diameter of the stand, different volumes, gross total volume, gross submersible volume, the BA, biomass, total above ground biomass, and density. And density is a challenge in the little bit. Like Andy talked about pruning, these predictors are very correlated with each other, so you have to be careful in which predictors you put in your model. Now on the Romeo project, we basically were very much a minimalist, and we pruned pretty heavily. In fact, we wanted to maximize only at 2 predictors because we had a very small data set, because it was more of a pilot on how to develop an inventory. We basically limited ourselves to a maximum of 2 predictors in our model so that we felt confident that the models would be fairly robust as we applied them across the landscape. We used seemingly unrelated regression, which has the ability for increased estimation efficiency and greater prediction precision, because it fits all these related equations. So whether you're predicting height, volume, basal area, quadratic mean diameter, they're all using the same set of LiDAR predictors generally, so different ones. But if we fit all the equations simultaneously, there's the benefits of minimizing the errors between the series of equations. Now, this was 2 years ago when we delivered the Romeo Millette inventory. Since that time, we're working on another 1 million hectare forest. We've also added saw log volume prediction, another volume that's looking at if we basically harvest out to the crown upper diameter limits, sort of the Crown Forest Sustainability Act, so our upper, say, a 10 centimeter top, what volume is available from the 10 centimeter to the tip of the tree in terms of biofuels? And so we're trying to estimate that. We're also looking at predicting the dominant codominant height, which better represent what a stand inventory height would be when an interpreter's looking at a stand. We're basically calling that. And the other one will be mean tree volume. So what's the mean tree size volume for that stand? As a result, some of the models became a little bit more sophisticated. We had a larger data set on the HRST to work on, but they're basically the same form in terms of the Lidar predictors are part of that. Some of the other things we've done on the HRST that we learned from the Romeo is we constrain things. The gross merchantable volume is a function of the gross total volume and sort of sets the maximum, so our model can't predict a gross merchantable volume above the gross total volume, things like that. This is the idea. These are one-to-one plots, that diagonal line being perfection, and this is for the black spruce. So if you look at how close the dots are associated with that diagonal line, you can see that for the different attributes of height across the top, merchantable BA across the top, and top height. So sorry, basal area. So this is basal area of all trees. This is basal area of all trees 10 centimeters or greater. This is height. For sure, LiDAR has no problem measuring height. Here's gross total volume, the quadratic mean diameter, which we are able to fit really well. Dominant, codominant heights, the next box to the right. Here we have gross merchantable volume, mean tree gross merchantable volume, sawlog volume, that close utilization volume, density working reasonably well, which one is that this approach typically doesn't do a very good job at in terms of predicting the number of trees. And then finally, the one that has some issues and a little bit of bias is total above ground biomass. So that's for one of the 9 sets of models we built on the HRST forest. And here's poplars, another example, a little bit, similar trends of doing a good job with these models. We're also looking at doing K nearest neighbors, and this is some of the results from the HRST forest. We have sort of that linear regression approach. We're also doing K nearest neighbors, and we're going to do a heads-up comparison and see how well they work and see if one has any strengths or weaknesses over the other. And as part of another part of the project that we're doing with some students in actually University of Chile. So basically, just to reiterate again, we basically have that 400 square meter cell. We go and get the point cloud data. We build models. We take that model and apply it to every 20 by 20 meters of the forest, because every 20 by 20 meters on the forest has that point cloud. So we have 100% enumeration of the standard of the land base. We have the ability to scale up the results. So we can predict for a 20 by 20 meters, or I can aggregate 2 20 by 20s, or 3 or 4. So I can go from 400 square meters to a block to a forest. At the end of the day, what we end up with is, we've seen these before, these are the rasters. This is a 20 by 20 meter resolution for all those different inventory metrics that we wanted to predict. So here we have heights predicted, top height 17.2 plus or minus 0.2 meters. Our gross merchantable volume on this forest is 102.1 plus or minus 6.3 cubic meters per hectare. Now, does the Alberta inventories have confidence intervals? Ontario's does. This is the first time we've actually put that type of estimation on our forest inventories because of some of the regression approaches that we've used in this. And again, if you're interested in how and why, that's in that forestry protocol.